Hello, Professor. This is the homework presentation. The topic is Lecture 2 Summary, and I am the presenter, Jiajun Jiang. And here's the agenda. I will start with the three main metrics to measure computer systems, which is cost, performance, and power. And then is Amdahl's law, Gauss-Fün's law, Flynn taxonomy, and the last one is risk versus risk. Here's the three main metrics to measure computer systems. The first one is die cost. The chips are more and more small nowadays. The smallest chips is only 2 nanometers. The company which made those chips is TSMC, a company from Taiwan. But why people want the chips become smaller? And what's the difference between 2 nanometer and 3 nanometer? The main point we want the chip smaller is money. When the chips are more tiny, the yield is bigger because the factory have many impurities. Even we already prevent the dust or other things fly into the factory, there are still some of them will affect the chips. We can see the picture in the slide. If we assume there are 3 impurities on the wafer, the left side have 9 chips, but the impurity makes 3 chips cannot use. So the total yield is 66%. The right wafer still have 3 impurities on it, but because the chip is smaller, the wafer can have more chips, so the total yield is 86%. The formula in the right side is to calculate the die cost and die yield and the cost of testing die. We are not only cannot sell the chips which have impurities on it, but also the more functional chips. There are different ways to detect the chips is work or not, but it is still a cost in the process. The final IC cost is package cost plus test cost plus die cost and shipping cost. The package not only can connect the IC chips, but also makes the heat dissipation. The way to decrease the heat is to increase the surface. And the package can protect the IC physically, like the moisture or some scratch on it. The package have 2 different materials. The first one is plastic, and the second one is ceramic. The plastic one is much cheaper, but the ceramic can provide a better heat transfer. The wiring type are different too. Those 3 have different pros and cons. The package also put all the chips in one package, so the package can contain many chips. The picture is contain 4 chips in one package, like the memory and the processor are in the same package. And then is the performance. The CPI and IPC is a number used to see a computer's performance. CPI and IPC are the same things. IPC is number of instructions executed while running a program over number of clock cycle required to execute the program. The CPI is the number of clock cycle required to execute the program over number of instructions executed in running the program. So the CPI and IPC is just they upside down the formula. So there's kind of the same thing. And the SPEC is System Performance Evolutional Cooperative. In the formula, we use trigonometric not arithmetic, because the program have different size. To improving the performance, we usually use parallelism algorithm. When use parallelism on n processor, we might think the more processor we use, the more speed up we get, but this is not true. The picture on this slide, we can see three different speed up. The green one is super linear speed up, which is pretty good, and the black one is linear, which means if you use more two processor, you can get 2 times speed up. And the red one is sublinear, which is more common in the reality, and we will discuss why this one will be the more common one. The M-DOS law was proposed by a computer scientist in 1967. The fraction enhanced, as the name suggests, means partial improvement. For example, my program has a total of 100 lines of code. 50 of them can be calculated in parallel. Then these 50 lines of code are fraction enhanced. The P in the formula is the propagation of parallel computing. N is the number of processes. When A equal to 0, which means the all lines is only 0, no parallel. So the speed up ratio S is 1, no matter the N is. When the N equal to infinity, the number of CPU cores increase, the ultimate accelerate will be the 1/1 minus P. For example, if the parallel code is 75%, the limited speed up cannot over 4, because you still have 25% of code cannot be speed up. For this, we can know that blindly increase the computing resource in parallel system cannot always double the overall performance of the system. And then is the Gustafson's law. Also explains the relationship between the number of processor, zero ratio, and acceleration ratio, but it is focused on different things. It can be seen from the formula, the N, which means the degree of serialization is small enough, that is, the parallelism is high enough. Then the acceleration ratio is proportional to the number of the CPU. And the power. The total power is dynamic power plus static power. Dynamic power consumption is mainly caused by the flipping of signal, which leads to parasitic RC charge and the discharge inside the device. While static power consumption is caused by the leakage current of the device when it is powered on. We have several ways to decrease the power consumption. The first one is voltage islands. Means we give the different IC parts different voltage, because not all the parts need the same voltage. So if we give the different voltage, we can decrease some power consumption. And the second one is power gating, means switching power to reduce the power consumption. It's like a switch. You can close it or open it. And the last one is dynamic voltage and frequency scaling. The DVFS technology is a effective energy saving technology that dynamically adjusts the operating voltage and the frequency of the processor to achieve a balance between system performance and power consumption, helping to improve energy efficiency, reduce power consumption, and then extend the battery life. So if you want high performance, you can give the device high voltage. And then is flame taxonomies. There are 4 different types, and there's no system designed by the NISD, and the NIND is the most common one. And then is the CISC versus RISC. In general, the advantage of the RISC architecture are that the instruction set is simple, fast, easy to design, and it is suitable for most embedded system and mobile device. While the advantage of the CISC architecture are that the instruction set is rich, powerful, and programmable. It's more easy to write the code. And the last is the reference. I search most of the resource from the wiki and some website. Those are really helpful for me to write the summary. So thank you, Professor.